Okay, good afternoon everybody. So, in this second class of our coordination compounds, we will see how we can utilize nicely the bond which is formed between the different metal ions, say with some species which will be termed as the ligands. So, this particular interaction between the metal ions, any metal ions, any source of metal ions, or sometime we will also find that the metal in the zero oxidation states, that means the atoms can interact with some smaller groups. Those can be very good anions or some neutral molecules. So, this particular interaction, if they are of the nature where we can get some interaction in terms of the coordination bond, we get the resulting coordination compounds. So, this we will see in this particular second class of these coordination compounds, and we were just discussing, taking example from your book, that when cobalt chloride, so basically cobalt chloride is reacting with ammonia, and why we are talking to say all these things is that if we have simple cobalt 2 chloride, we all know that is a solid compound. So, cobaltous chloride. So, this cobaltous chloride, when we react with ammonia, we will find that cobalt ion can form some interaction coming from the lone pair of electrons on the ammonia molecule, because ammonia we all know this is typically a pyramidal molecule. So, where these Cl minus will be there and how these are from the solid state, that means this is a solid compound. So, solid state identification of these things where the metal ion is only present in the bivalent state and the chlorides were there, like the regular packing, what we all know the rock salt structure of sodium chloride say. So, when we come for the solution, so this is a very good example to study some interaction for knowing the solution chemistry. So, solution chemistry for all these will be very much informative in terms of the corresponding availability of these chlorides, because these chloride ions will also be available to us as the same ligand. And definitely if the concentration, depending upon the concentration, if the concentration is not that much, the available chlorides will be less, and if we add this, because this concentration is higher, that concentration of ammonia molecules are higher than that of our chloride ions already available here, because we are not adding any externally the chloride ions, that means the sodium chloride or any other thing we are not adding as some external source of chloride ions. So, basically these ammonia molecules will try to gather around the cobalt center and will start interacting with this particular cobalt center through the well defined dative bond between nitrogen of ammonia and the cobalt center, which is in the bivalent state. So, how we can identify these compounds? So, the coordination compounds will give rise to different compositions that we have discussed in our previous class, that how we can analyze these compositions in terms of the availability of this chloride, where because we have defined also the primary valence and the secondary valence, whether this chloride is available attached to our cobalt center, where or they are remaining outside the coordination sphere, because whatever we have inside this particular square bracket, this square bracket, the metal center will be attaching with so many ammonia centers. So, if it is number is 6, we have a regular octahedral geometry around this cobalt center, and this particular thing, that means the whole entity, the coordination entity we get as the corresponding coordination sphere. So, how this coordination sphere is forming and what is the nature of these things, and also these chlorides which are staying outside is required for charge neutralization. So, this is required for charge neutralization. Then we will just use something, that means, since we are doing everything in solution. So, we dissolve some amount of this compound once it is formed in the solid state, and we know the concentration of that compound in that particular solution. So, wherever we make any solution, we all know that certain amount of solute will dissolve in a certain volume of the solvent, giving a particular concentration, and that particular concentration is important to know something which will be now tagged as the solution molar electrical conductivity. That means, this is the cationic part and these are the anionic part. Like the salt, we all know the sodium chloride, the calcium chloride or aluminum chloride, we basically compare them in terms of their corresponding lambda m values. So, lambda m values, that means the species which are available, the ions which are available to carry the electrical charge from one electrode to the other, that will give some idea, that means the how many of those species, the charge carriers, are available to carry those electric charges, and that will immediately distinguish whether your chloride is outside the coordination sphere or inside the coordination sphere. So, that we get this example from this particular table. So, we have the yellow compound, the purple compound, the green compound and the violet compound, but you see the number of chloride ions which are outside the coordination sphere are different. In the first case it is 3, in the second it is 2, and two other cases this is 1 and 1 only. So, if we measure the solution electrical conductivity in terms of the lambda m values, the capital lambda m values, we can define them as their nature, that the electrolytic nature of this electrolyte is 1:3, 1:2, 1:1 or 1:1, like that of our aluminum chloride, calcium chloride and sodium chloride. So, we must have some good idea about that, where the chlorides are, and that will also differentiate, that means the color of the species and its electrical conductivity, and we can identify this. So, it is one of the property which can be readily used to identify a particular type of compound, because this molar conductivity at a particular concentration is related to the number of moles present. So, if we consider that we are going for a 10 to the power minus 3 molar solution, we calculate out that particular specific conductivity, and then by multiplying the molecular weight we get the molar conductivity. And that is also immediately known to us whether a particular complex is electrically neutral also, because sometimes we find out that from some particular type of reaction we get the compound and which is separating out, which is not so soluble in water medium or the alcohol medium or the water like solvent medium. The compound which is precipitating out is also a coordination compound with a neutral character, that means no charge is there, either cationic or anionic, and they do not show any electrolytic behavior. That means their lambda m values would be very less, sometimes it is very close to 0 only, and that also immediately characterize the electroneutrality of those compounds, and we can write down the formula very easily. So, this basically is formed, and we can define that a metal complex or the metal ion complex is formed when this particular hexaamine cobalt 3 chloride is forming, and some of these, that means the chlorides are going out which were originally present with the cobalt salt as the chloride salt of cobalt. So, chlorides are not taking part in the complex formation, and they are only held in ionic forces, and the solution molar electrical conductivity measurement gives us some idea that this is a typically ionic compound in the form of that is the cationic part is a complex part, and the anions are simple chloride ions. So, that we can remove these chlorides as silver chloride also, that we have also seen. So, not only the transition metal ions or 3D block elements, or sometimes we can also consider that the F block elements or the lanthanides or actinides, but also the main group metal ions and sometimes the main group metal atoms also can give rise to this sort of interaction, that means the coordination compounds. And as we have discussed already, so this we are basically again recapitulating what is the primary valence and the secondary valence, the two types of valences we get, and one will be directly related. The primary valence corresponds to the oxidation number and the secondary valence is the coordination number. What does it mean? That if we know the primary valence, that means the primary valence which was originally there for the cobalt salt, which was therefore the cobalt as the corresponding cobalt chloride. So, we have the formula of the compound as COCl3 dot 6NH3, and sometime we also find that this number, the number 6 is varying depending upon the number of molecules, that means the ammonia molecules surrounding the central metal ion center. So, if we now see that particular primary valence, so PV if we say the primary valence corresponds to the typical oxidation number, which is also true for the salt itself when we use this particular salt, but here the reaction we do basically from cobaltous chloride, and the oxygen from the air is responsible for the oxidation of the cobalt center, because in presence of ammonia the E0 value, the redox potential for the cobalt 2 cobalt 3 is less, which is higher in case of bound water molecules, but when the water molecules are replaced by ammonia, the E0 is less, and which is achievable by the simple oxidation of the dioxygen molecule which is present in air. So, this is getting oxidized. So, if we now consider that particular formula of that compound, that how many chlorides are there outside this coordination sphere. So, outside this coordination sphere, the number of chloride ions will tell you the corresponding oxidation number. So, since we are starting from a salt which is in the lower oxidation state, that means the cobaltous ion, and that cobaltous ion is getting oxidized. So, if that particular compound, the complex compound what is formed over there due to the reaction with the ligand's ammonia, if that is forming still with that of the lower oxidation state, that means the oxidation state is still cobaltous, will be getting 2 chlorides over here, and this particular oxidation state will give rise to the corresponding charge on it. So, the primary valence is also responsible for the charge on the corresponding complex species, and which is neutralized by the corresponding number of anions. So, sometimes it so happens that this particular part is forming, but due to the non availability of right number of chlorides, the compound is basically the complex cation is not separating out as a precipitate from the medium, as a solid precipitate from that particular reaction medium, which can be water, pure water, or which can be a water alcohol mixture or something else. So, this particular thing is that you have to supply or you have to provide the corresponding anions to know this thing. And what about this coordination sphere? Because here we find that in case the inside this thing, that we are having 6 such nitrogen cobalt bonds. So, 6 such cobalt nitrogen bonds will be forming over there, and which is related to our secondary valence SV. So, secondary valence will be equal to then the corresponding coordination number. So, one is the corresponding oxidation number. If cobalt is trivalent, the number of chlorides outside the coordination sphere will be 3. If it is 2, it will also be 2, but difficulty arises due to the nature of the corresponding metal ion or the metal atom to identify the corresponding coordination number. So, that will also related to our formula, how we write the corresponding formula and how we get the formula and the corresponding number of ligands which is surrounding the central metal ion. So, what we see here that COCl3 6NH3, thus according to the Werner, the Alfred Werner defined that thing, the cobalt has 2 valences and one is 3 and another is 6. So, immediately we will have some good idea about the number of groups which are surrounding the metal center and the number of outside groups which will be required to separate that particular compound as the ionic solid. So, these are also very good ionic solids. So, coordination compounds are the corresponding ionic solids. So, the entity which is forming within the square bracket is your coordination entity, and it has the central metal atom or the ion and bonded to a fixed number of ions and molecules, because the ligands can be ions and ligands can be neutral molecules. So, what are those central atoms and ions? It is the atom or ion which has a fixed number of ions and groups bound in a definite geometrical arrangement. So, we can have a typical geometrical arrangement, and we will see that the corresponding geometry is also related to the corresponding CN values, that means the coordination number values. So, what is that coordination number? Then we basically bring the idea of the ligand. So, the ligand with that of your donor atoms, if it is water molecule, it is the oxygen atom which is responsible for donation is charged through its lone pair of electrons to the central metal ion. If it is ammonia, it is the nitrogen of the ammonia molecule which is directly forming bond to the central metal ion. But if it is species like PtCl6 2 minus, where you see that we know that the simple platinum salt which we get, that the platinum chloride. So, if the platinum chloride we get, so is a typical salt like nickel chloride, so is a bivalent one, then as a complex species we can have PtCl4 2 minus, and also another species what we are writing over here is PtCl6, that is also having a charge of 2 minus. So, what does it mean? Is a very interesting thing that how you get it. We know is a simple metal ion salt, which is also true for other metal ions like nickel chloride, palladium chloride and etc. And here we get something which is a coordination compound. And this coordination compound, we have a platinum center, and we should know the corresponding oxidation number. Therefore, since the charge is 2 minus, how we are getting this? So, if the palladium is also bivalent like this palladium chloride, this is also a palladium in a bivalent state, and 4 chlorides are surrounding this platinum center and giving rise to a overall charge of 2 minus on this particular coordination sphere. But what about this particular species, where you see the corresponding coordination number has also been changed and the charge is also of the same type. The chlorides has changed, the number of chlorides present with the platinum center is more, but still the charges are same. It is also 2 minus than which was also there for this other species as the 2 minus. So, definitely this is a oxidized form of platinum. So, platinum in the tetravalent state can give rise to a corresponding coordination number of 6, which is not so common. So, there should be some relationship. We therefore see that the relationship between oxidation number and the coordination number, as we move for, that means as we are able to oxidize the center, it can assemble more and more number of anionic groups particularly, and if it is not available, it can also try to gather the more number of this corresponding dipole, the negative dipole of the neutral molecule as the ligand surrounding the central metal ion. So, this is an interesting observation, and how we can isolate this particular compound as salt also, and this particular compound as salt also we should know. So, in this particular case, what we see that the second example where we get the nickel, when we dissolve any nickel salts, a nickel sulphate or nickel nitrate in water, and with that then add ammonia, we get this species, this particular species. So, initially we get that some species is forming like this, and sometimes it can also change to a corresponding coordination number to 6 also, but initially it can also form a species like this. So, here this corresponding CN value is 4 for nickel. So, this has been defined. So, first time this is another Alfred's talk in around 1960, not in relation to the coordination chemistry of the metal ions, but also for the silicon chemistry, first defined this particular thing which is interacting with the silicon center, which is not a metal purely metal center, is a metalloid center, but which is interacting with some other groups like nitrogen or oxygen. He coined the term ligand from the Latin word ligare. Ligare is to bind, that something is binding to that particular center. So, that is why it is open up to so many things. That means, whatever species starting from your solvent like water molecule, the methanol molecule or the acetonitrile molecule, which is an organic solvent, we can label them in terms of the coordination compound that they are also our good ligands. So, there can be small ions or molecules which are able to bound to the central metal ion or the metal species, like that what we just now discussing about the chloride ion, and the small molecules like water, when we use water as a solvent for the preparation of any solution, or when we add the dilute solution of ammonia as the base also, and we define something that some larger organic molecules or sometimes even macromolecules can also be ligands. So, what does it mean? That if we go beyond this ammonia is NH3, but this is the amine function on a organic backbone. So, it is basically NH2 CH2 CH2 NH2 is nothing but your ethylene diamine. So, amine, the ammonia is a typical amine, or we can go for methylamine or the ethylamine or sometimes the triethylamine also, which is also a base of different quality or different character. So, what happens to this particular base, that this nitrogen is available to interact with the metal center. We will see that whether the other part of the same amine, which is a small one, whether the other part is also available to bind to the same metal ion or a different metal ion, or it remains dangling or hanging. Similarly, this is also another different type of tripodal amine. With this nitrogen like ammonia NH3, we know that N is there. Instead of 3 hydrogen attached to that, we can have the ethylamine arm. If we add 3 ethylamine arms to it, so that particular ethylamine arm can give rise to some species which is also ammonia like. That means ammonia like pyramidal. So, that pyramidal environment also available with that of the lone pair pointing towards the different side above that corresponding site, we can get the corresponding species as the ligand, and also the protein part. So, we all know that the proteins are amino acids, the building block of proteins are amino acids. So, the carboxy function, the acid function as well as the amine function, ammonia NH2 function is there. So, that is why like ammonia, like ethylene diamine and like this tripodal amine, the nitrogen of this protein part or the nitrogen from some other groups from the protein chain, like that we know in our blood in hemoglobin and myoglobin the histidine residues are there, which is having imidazole side chain. So, the backbone is forming through the carboxy end and the amine end of the amino acids to give you dipeptide, tripeptide or the polypeptide, which are the typical backbone of the protein structure. But we can have nitrogen, we can have oxygen and some other pendant groups which can also be available for coordination to the metal ion center. So, in case of proteins, the versatility is more depending upon the nature of the protein structure or the amino acid pendant groups. Those groups will be available to coordinate to the metal ion center. So, these are very simple example what we can have. The water already I discussed a lot, then ammonia, then the chloride also, which is a very good spear like arrangement having one charge. Since the size is very big, initially what we can see that the one lone pair of electron can be available to bind to the metal center, but theoretically as we want to predict it whether it can have some bridging aptitude or whether all 4 lone pair of electrons around chloride ion will be available to interact to the metal center. In fact, it is possible you can have some in a particular situation, you can have entrapped chloride inside some cage like arrangement where all 4 lone pairs of electrons can interact to different metal ion centers like M1, like M2, M3 and M4, giving rise to a tetranuclear complex where this chloride ion can function as a nucleating bridging group in mu4 form. That means, in the mu4 binding mode is available for this chloride ion to show its ligating behavior. And this is a small gas molecule like dioxygen molecule. What we all know that the dioxygen is also interacting to the iron center in our blood molecules. So, this is the carbon monoxide, as we have seen, is nickel tetracarbonyl, which is in the 0 oxidation state of nickel. This is forming some interaction through this carbon end, the lone pair on the carbon side, because oxygen is more electronegative and this particular thing is forming or stabilizing the low oxidation state, that means the nickel in the zero oxidation state, forming that particular carbonyl compound. So, not only nickel carbonyl, we can have the interaction with the other metal ion center, the metal in the zero oxidation state, that we will see briefly for those compounds which are the metal carbonyls. So, some mononuclear metal carbonyls are known, as well as some binuclear metal carbonyls are known for the 3D elements, that we will see afterwards. So, how many donor atoms we can have? So, this ethylene diamine have 2 donor atoms, this is one NH2 and the other NH2. So, the ligand can be bidentate. Similarly, if we go beyond 2, we get tridentate, tetradentate and polydentate behavior. So, this is some good example from those ligands. So, we should immediately know some good molecules, and these molecules whether they are showing some interaction to the metal center, like this carbon monoxide, this chloride. Similarly, the cyanides, the first example what we have taken is the corresponding ferricyanide and the ferrocyanide ions also, and their cyanides are the ligands to the iron center. Similarly, this thiocyanate, it has a very good value in terms of the corresponding analytical chemistry, because when we add thiocyanate, very dilute solution of thiocyanate to any iron solution in the ferric state. So, ferric solution when interacting with this thiocyanate, giving rise to a very good or blood red coloration, which is very much characteristic for this corresponding identification of that iron center, and water already we discussed this. Then the example for the bidentate ligand, which is also useful, that means one end and the other end, if the molecule is like this. So, it is basically not a strictly linear molecule, but is a zigzag type of molecule, because this carbon is tetrahedral, this carbon is also tetrahedral. So, in the zigzag way you can have this thing, but if you bring this nitrogen around the same metal center with along with the other one, we get a cyclic arrangement like the any other organic molecule, the cyclic type of arrangement. What do we see here? So, if your center is any cobalt center, that means the cobalt in the +3 state. So, one of the ethylene diamine, this ligand, you see this is a typical bending mode of binding. So, is forming a particular 1, 2, 3, 4, 5 membered ring, which we call as a chelate ring. So, chelate is the typical binding, claw is the binding. So, is basically binding through these 2 nitrogen. So, these 2 nitrogen heads are coming close to each other for binding the metal center, which are basically this angle is 90 degree, that means the cis angle around the octahedral geometry. So, this cis angle which is occupied by one of the ethylene diamine molecule can also be extended to two other cis angles, basically giving rise to a compound which is octahedral in geometry, having 3 bidentate ligand instead of 6 monodentate ligand. Earlier we are seeing that if we have a octahedral complex, we require 6 monodentate ligands like water or ammonia. Now, since the ligand is bidentate, we require 3 of them. So, we call them as, since 3 of them are present, we call them as the triskeleton complex. So, this is the most abbreviated form, that means we do not write the details of these donor groups, but the binding basically we write in this fashion, and what we see that is a particular type of binding. So, is basically the 3-dimensional view we should visualize always whenever you are writing any complex in this form, that means the triskeleton we are writing. So, basically you write in this fashion of a propeller type of arrangement. So, this propeller type of arrangement is also very easy to visualize. So, this is one form, and the other form we can also get, that means instead of connecting this with this point, we can go back, that means we can go to the other side. So, this point can go to this side, similarly this can go to this side, that means the other open ends can be occupied, which can also be a typical mirror image of this one. So, if it is in the left hand side, if we put mirror over here, we can get another image on the right hand side, and these two will have some interesting property that we will see, because it is a much more complex geometry compared to your carbon center, where we apply the chirality on the carbon center, the optical activity on the carbon center. So, in terms of this metal ion center, this particular cobalt center and all these metal ion center, whether we get these as the corresponding thing, that means the chirality we can have, and that particular chirality we get in terms of the corresponding coordination which is octahedral in nature, and we have the 3 bidentate chelating groups attaching to that particular central metal ion. But if we extend it further in terms of something what we will talking in terms of the corresponding backbone. So, this is a basic example of a polydentate, but exact definition for that particular ligand is hexadentate. That means, this particular ligand has 6 donor groups. So, this nitrogen and these are the charged oxygens. So, this charged oxygen and this charged oxygen and another charged oxygen, another charged oxygen, because the overall charge of this particular species of the organic molecule is 4 minus, which is the corresponding tetranegative salt of ethylene diamine tetraacetic acid. And sometimes we get this as the corresponding disodium salt. So, disodium salt of ethylene diamine tetraacetic acid, which is a white crystalline compound, can be in our hand. So, what is the nature of this denticity of this particular ligand? So, 2 nitrogen, if it can donate to the metal center, we can have this oxygen, we can have this and this oxygen. That means, 4 of these oxygen atoms can also be available to coordinate to the metal center. As a result, what we get that the bidentate or the polydentate, that means the tridentate, tetradentate and the hexadentate ligand, they are all chelating agents, because they hold the metal like a claw. So, again like that of a definition for the ligand for the Latin word. Now, the Greek word chele is used for the claw, which is using for the chelating one for the coordination to the metal center by a bidentate ligand. So, if we consider this lead, so not that we can have calcium also, we can determine the calcium in hard water by doing some analytical chemistry, which is known as complexometric titrations. So, this particular complexometric titration is also useful, because we know that just now I told you that the disodium salt of EDTA is a very good reagent, which is a solid reagent. You can take some amount of that solid and you dissolve it in water, such that you get a standard solution of this particular ligand. And when we use, instead of lead, if we have the calcium or magnesium in some water sample, that means we are talking something which is related to the hardness of water. So, we can determine the hardness of water by determining the calcium 2 plus and magnesium 2 plus in water. We basically do not want these metal ions to be present in water when we use soap or detergent to get good leather. So, this can be avoided. So, this particular one, so these metal ions in our hand, not in hand, it is in water. So, everywhere if the source of water is not so good, we can have calcium or magnesium, and sometimes we find that the industrial effluent water can also contains or contaminated by calcium 2 plus and magnesium 2 plus. So, the metal ions will be in our hand, and if we use EDTA 4 minus ethylene diamine tetraacetic acid. So, this is our hexadentate ligand, and we have seen that this particular one having this ethylene diamine backbone. So, that ethylene diamine backbone will then tell us that it has 2 nitrogen along with 4 oxygen. So, these are the abbreviated form of that ethylene diamine tetraacetic acid. So, when it binds basically, so we get a calcium N2O4 complex, and how we immediately draw basically. So, drawing of this is also very important, because we are correlating the binding of this EDTA, that means the hexadentate ligand to the calcium center or the magnesium center. So, since these 2 nitrogens already we have seen, they can very easily form a bond which giving rise to a 90-degree chelation. So, this particular around 90-degree chelation, these are the cis angles. So, these 2 are occupied. Then we can have 4 other points available. So, we have to fit this particular molecule over here. So, what we get, this nitrogen extended with this oxygen and this another one with this oxygen. Similarly, this nitrogen will come for this oxygen and this nitrogen will come for this oxygen. This particular one will have a total charge of 4 minus, calcium is having 2 plus. So, overall we can have some charge there again. So, this is 2 minus. Since we are talking all these things related to something where we consider these as the corresponding species forming in water, because we are determining the hardness of the water which is contaminated with calcium and magnesium. So, water, some metal complex or the coordination complex species is forming due to the availability of these, which can also give rise to the corresponding standard solution. You can weigh out the standard solution and we can quantitatively determine the amount of calcium 2 plus present in that water sample. So, in water the coordination compound which is forming and which is anionic also, that is why that will also be in the soluble state. So, that give rise to something which like redox titrations, like your titration with permanganate, titration with dichromate, we call this as a complexometric analysis using complexometric titrations. So, like redox titrations, we can have the complexometric titrations, where if we know the standard solution, that is the known strength of this solution of m by 10, then we can find out the unknown concentration of this calcium which is present in the water molecule. So, that gives rise to a very good example for this, and also this particular information can be extended if we consider that if we have something that some metal ion, that means the lead, which is not good for us, the lead is a poison one also. So, if somebody is affected due to the lead poisoning in their in his or her body, so if this particular species, that means this can be added as a corresponding medicinal value, that it can go to the body and bind lead nicely, such that this particular species can take out from your body through your urine, and such that the lead poisoning or lead contamination can be avoided. So, starting from the analytical chemistry application of this EDTA, we can have some medicinal value of that particular EDTA, because EDTA is present everywhere, it is also present every day, we use in toothpaste also. So, this chelation basically gives rise to something. If we write this EDTA as this, the metal EDTA complex where the stoichiometry is simply 1:1, just now what we have shown to you. And when we get this, so when EDTA is forming, this is not right, this should be 2 minus, since this 2 plus is there and 4 minus is balancing. So, what we here I am trying to tell that if you have two species in solution on one side, so this is one species, because this is also present as a corresponding aquated species where 6 water molecules are bound to the metal center. So, this is a complex species. So, hexa-aco metal ion, corresponding hexa-aco metal ion species in the bivalent state is one particular species which is also interacting with the EDTA, and right hand side what we get, we basically get 7 species, because 6 water molecules will be losing from the coordination sphere or the coordination environment of the metal ion on the other side. So, that is why there will be a energy gain from the free energy gain from the thermodynamic point of view, because the magnitude of the delta S is different. So, entropy is rising on the right hand side. So, that basically gives us some idea why this reaction is moving from left to right, that is the driving force for that particular reaction for EDTA coordination, and that also gives rise to some idea why we call it as a chelation therapy. So, this chelation therapy gives us some idea in terms of the corresponding removal of lead as lead 2 plus, mercury as mercury 2 plus, and cadmium as cadmium 2 plus. Just now what we have seen, the corresponding complex which is forming with lead 2 plus. Similarly, the mercury will also, though it is not favorable for a octahedral complex, which is also not true so much for cadmium, but if we force, if the ligand is forcing us to take corresponding stoichiometry of 1:1 only, so the metal will have no other option to interact with that particular ligand. Basically, it is getting trapped inside the ligand, which is providing 6 donor atoms. That may be not good bonds forming around mercury and the cadmium, but it will be trapped inside, and the stoichiometry of 1:1 is also valid for these two species there. So, like lead also this is wrong, this is 2 minus. So, for the lead what I have just now shown to you is also the corresponding thing. So, lead which is a poisonous thing for our body, which can kill our cell, the cellular destruction can happen, but this is not so poisonous. So, body can excrete from the body without any problem. So, that is why the EDTA is helpful. If it is present in our toothpaste, it is also helpful if some amount of lead or any other metal ion like mercury or cadmium is there in our body, which can be removed nicely. So, the species what is forming due to the removal of these and which is known for its chelation theory. So, chelation we are utilizing for some amount of therapy. So, the therapeutic application. So, next item what we can talk about is the coordination number. Already we defined that the number of ligands surrounding that particular metal center. So, the donor atoms which is provided by those ligand to the metal or the metal ion is directly bonded. So, that gives rise to the corresponding coordination number, which is a typical coordination number. So, we will start from a typical coordination number of 2. So, we will have some thing that why we are not asking us that whether we can have a coordination number of 1, which is 2 will be has a reality. So, is basically if we can get something that whether we can get something coordination number of 1. That means, if we have a metal ion which is N plus, we can show one interaction with that particular metal ligand. So, basically this particular one from starting from here to there, that means you have something, that means your metal ion is basically trapped and it has no other donor groups available to coordination to the metal center. So, it is basically something where the metal ion is only trapped, but is not showing any other coordination or some bulky groups. So, bulky hydrophobic environment which is not showing any bond to the metal center is surrounding that metal ion, then only one point of attachment is available. Then some small groups can come and interact with the metal ion center. So, that can be the typical example for a coordination number of 1, but which is not of much reality. So, we will start our thing, that means the reality is from coordination number of 2, which is there, that means the ligands are there, metal ions are there, and it has a good reality. So, this coordination number of 2 is the typical one where the thing is that we can write Ag NH3 whole 2 in square bracket having a charge of 1. That means, silver is present in monovalent state. What we all know, this particular species is forming for the analytical identification of chloride ion in solution, because chloride we all know that which can be precipitated by adding silver nitrate with a white precipitate of silver chloride, which is soluble in excess ammonia. So, what does it form? That silver chloride which is forming over there is solubilizing in ammonia. That means, the species what is forming, the way we are doing all our discussion on cobalt chloride with ammonia, similarly silver chloride is interacting with our ammonia, giving rise to the corresponding ammonia complex. So, the driving force is that formation of AgN bond instead of the simple ionic solid as the silver chloride which is precipitating out from the medium. So, that gives rise to something which is also similar. So, any silver thing, why we are talking all these things here is that the example of silver, the identification of that particular silver is very important, and that silver will tell us that whether we can get something for some other reagents. So, silver based reagents also we do some organic chemistry reactions or the organic analytical chemistry, there we find the preparation of tolerance reagent. So, that tolerance reagent is also that we can have the silver. So, silver as the silver nitrate and preparation of that tolerance reagent can also be helpful, because we most of the time we use the tolerance reagent, and the laboratory you are supposed to know that particular reaction for the tolerance reagent. So, is we by name it is called as the ammoniacal silver nitrate solution. So, what does it mean? The ammoniacal silver nitrate solution, what we can prepare is that if we have a solution of silver nitrate, so silver nitrate is treated with a very dilute solution of sodium hydroxide, giving rise to the precipitation of silver hydroxide. So, the medium is typically alkaline due to the presence or appearance of silver hydroxide in the medium, and like silver chloride, we just dissolve it in ammonia. So, ammonia solution is next added, giving rise to AgNH3 whole 2, which is the corresponding complex species. If outside the hydroxides are there, the hydroxide will be balanced. So, what we do basically, we are getting this particular one. So, this is your ammoniacal silver nitrate solution is the Tollens reagent, which can be reduced for some other reactivity pattern, which is derived from your silver nitrate. So, this particular species as immediately tells us that it has the corresponding coordination number of 2, because the silver ion center is there, which is forming only 2 bonds with the ammonia molecules, and which is the linear one having 180 degree nitrogen silver nitrogen bond angle. Similarly, we can have other example for CuCl2 minus. If the copper is present in the cuprous state, like silver, we all know that the copper, silver, mercury and all is the typical triad. So, copper also not in the bivalent state, because the bivalent state, once we know that the oxidation state, if we change the oxidation state, its corresponding coordination number and the corresponding other groups which will be attached to that particular center will also be different. So, this particular cuprous chloride is also like that of our silver. That means, you have a linear arrangement of 2 chloride groups attaching to your copper center, which is not true for our silver. Silver is silver chloride, but is not so easy to get AgCl2 minus over there. Similarly, the other very good ligand to these metal ions is the cyanide ions, because the cyanides is a good processing reagent for the recovery of metal ions from its ores for silver, for copper, etc. So, the species, the corresponding species, if instead of chloride, if we can have the cyanides, it will be CuCN whole 2 minus. So, that is basically coordination number 2, and the coordination number 3 is also not very common, and we will not discuss here about this coordination number, but typically if we consider a particular type of metal center, and again if only 3 points are available, that means a T-shaped arrangement or a regular trigonal arrangement, then only we can have a corresponding coordination number of 3. Then the coordination number 4, immediately what comes into our mind, that if we have a coordination number of 4 and if we place 4 groups around this metal center, we get a corresponding tetrahedral arrangement, which is more common, and the other one is the corresponding square planar one for the D8 electronic configuration. That means, we will see for the triad of Ni2 plus, the bivalent nickel, the bivalent palladium and bivalent platinum. These are all in the series of the D8 electronic configuration. They can have this particular arrangement, and the other alternative arrangement is the corresponding tetrahedron, formation of the tetrahedron, and we all know that there are a large number of tetrahedral cobalt 2 complexes. So far we are discussing cobalt 3. Once we get it as a cobalt 3, we stabilized in the octahedral geometry. So, the coordination number is high when the oxidation number is also high, which is trivalent in nature, but if the oxidation number is less, which is +2, we can restrict the corresponding compound to a tetrahedral compound, and this is the well known example. Already we know this about the tetracarbonyl species of nickel 0. So, it has a tetrahedral geometry, not a square planar geometry. So, it is basically preferring a geometry where the corresponding hybridization scheme, we will see about the corresponding valence bond structures and all this when we study that this particular arrangement is favored compared to your square planar arrangement. Then if we write something, that one particular compound, that we instead of write this thing as the tetrakis. So, bis, tris and tetrakis, we all know that the nomenclature what we are using, that means when we have the 2 ligands, we call as the bis. Already if we the name contains some ethylene diamine type of things, ethylene diamine is the abbreviated version of the ethylene diamine. So, ethylene diamine. So, di, the term di is already there within the name of that ligand. So, when number of such ethylene diamine present around the metal center is more, that means we have 2 ethylene diamine moieties, we can call it as a bis ethylene diamine complex of that particular metal ion. So, we will bring that base. Then similarly, if we have 3 such species like that, we just now we have seen that if we can have the cobalt tris ethylene diamine cobalt 3. So, which is a tris complex. So, this means we have 2 ligand, 3 tris means we have 3 ligand, then tetrakis will immediately tell us, if we know the number, that it has 4 groups of those ligands surrounding this particular center. So, tetrakis, triphenyl, phosphine, palladium, and just if we miss the oxidation state, we should also be very much careful about the oxidation state. If this is missing, that means the palladium oxidation state is not given to you. How you can identify that what type of oxidation state you can have over there is that you have this particular one. So, what is the nature of this ligand? So, you should be able to know what is triphenyl phosphine. So, triphenyl phosphine is nothing but PPH3. It is like ammonia, where ammonia is there, nitrogen attached to 3 hydrogen atoms. Similarly, if the phosphorus is there, like phosphine is analog of phosphine, where you have the pH, because instead of this pH bond, we have now PPH bond, that means P carbon bond. So, that P carbon bond has some extra stability, that is why it is a very good ligand and very useful ligand. Useful monodentate ligand. And if we surround these as the 4 number, so if you have the tetrakis, triphenyl phosphine, so like ammonia, we are not able to get any charge out of this triphenyl phosphine. So, therefore, if the overall complex is neutral, then palladium must be in 0 oxidation state, and that is the corresponding affinity like that of our carbonyl affinity to the nickel 0 center. So, the palladium also has some affinity, palladium 0 also has some affinity to triphenyl phosphine to give you the tetrakis triphenyl phosphine compound. So, this is the very beautiful compound in a petri dish. We call this dish as the petri dish. So, petri dish, the sample we usually take out it and is the very beautiful color. So, coloration what gives us, that is also something that you have a triphenyl phosphine compound of palladium, where 4 such triphenyl phosphines are attached to this, and it has some good role to play in organic chemistry, in industrial chemistry, because it will have some catalytic role. And the same tetrahedral arrangement, here also you have the same tetrahedral arrangement we get, having some this triphenyl phosphine, which are basically some amount of umbrella. So, this is basically entrapped within the arrangement of 4 triphenyl phosphine units. That means, these are, if we consider that is a threefold symmetry, that is one umbrella on this side, the second umbrella on this side, the third umbrella on this side, and the fourth one on the other side. So, you will have basically a 4 umbrella, and which basically trapped inside, because each triphenyl phosphine have 3 phenyl rings. So, 3 into 4, 12 phenyl rings are surrounding this particular nickel center, which is basically entrapped within a very good organic moiety, which is connected through phosphorus atom. So, the other alternative for this coordination number of 4 is the square planar arrangement, and is very much important that if we just consider that corresponding compound, which is NiBr2 PPH3 whole 2, which is very good a catalyst, and which is used by this scientist Walter Rappe for the synthesis of acrylate esters from alkyne carbon monoxide and alcohol, which is very good application for this. But is again like that of our palladium center, is a basically typically a compound where your 2 bromide centers are there and 2 of them phosphates, and they will all be in the planar arrangement. So, if we just consider these 2 are phosphorus groups and these 2 are bromide groups, is basically typically a corresponding planar arrangement. But in case of these chloride groups, that means if we bring these from bromide to chloride, we get this, which is a tetrahedral one, and complex of nickel, which is spin triplet. That means spin triplet is nothing but you have 2 unpaired electrons, and the multiplicity we all know that the corresponding capital S value is 1, and the corresponding multiplicity of that spin state will be twice S plus 1, which will be equal to 3. That means is a paramagnetic compound and paramagnetism of 2 electron, which give rise to the identification that it is a tetrahedral molecule. But if we consider that it is not that for palladium, it will be square planar in arrangement. So, we get that as the contrasting thing for these two compounds. One is the corresponding chloride compound around nickel and another is the chloride compound around palladium, and in the palladium size is basically dictating and the corresponding bond for the palladium phosphorus is also dictating that you will end up with a square planar arrangement. You will have some theoretical justification also when we talk about the bonding in terms of valence bond theory and the crystal field theory, but now you can think of it as a experimental reality. If you do the reaction, we will end up with this product which is tetrahedral in nature, in shape, in geometrical shape, and this will be square planar in shape. Then the next one will be your penta-coordinated one, which is a very nice compound of acetyl acetone, again useful bidentate ligand. Only thing that the stability on VO, the V double bond O, the VO double bond part is taking out, and this particular part is very useful to understand that you have a square base coming from that double oxygen bond of the acetyl acetone group. So, this is the double oxygen from the acetyl acetone group, and this is the other end of the acetyl acetone group, which is the bidentate O ligand. The other one is also a bidentate O ligand fulfilling the square plane, but the square plane is not perfectly square plane because the vanadium will be little bit above of this particular square plane with a corresponding vanadium oxygen double bond. So, towards this vanadium oxygen double bond, this vanadium is little bit above to this particular square base, which is formed between the 4 oxygen of the 2 acetyl acetone moiety. And the reaction is also very simple from the experimental point of view, that we can react it with directly with the vanadium pentoxide, and the vanadium pentoxide is basically getting reduced to a vanadial compound of acetyl acetone and with the oxidized form of the ligand with the elimination of so many water molecule, and it has also some application. So, the application wise this particular compound not only in terms of knowing this as the corresponding metal complex, but is also very useful in understanding its ability as a catalyst, because V2O5 we all know which is required for your contact process of making sulfuric acid. So, vanadium is a very good catalytic site in terms of the metal ion, and we can exploit that particular reactivity of this vanadium center by binding to a ligand which is a bidentate ligand, not like your ethylene diamine, but is acetyl acetone ligand, and you go down to another oxidation state which is a tetravalent oxidation state, and that tetravalent oxidation state would be useful for a typical epoxidation reaction of allylic alcohol in combination with some tertiary butyl hydroperoxide, because this hydroperoxide is responsible for some double bond, CC double bond, some allyl group is there. So, allylic alcohols are there. So, allylic alcohols are there like allylic amine. So, this double bond can be going for the corresponding epoxidation using the tertiary butyl hydroperoxide, which is the source of organic peroxide supplying that oxygen for the epoxide formation. Okay. So, this is the example of a coordination number of 5 for a particular metal ion, and as a catalyst its application because the center is vanadium. Okay. Thank you very much.